All right, now for the Zoom meeting, the most important thing at these Zoom meetings is to go over some example problems. So this is the Zoom meeting for January 19th. That's what, the end of the second week. You've been reading chapter 21, which is on motion in one dimension. The important thing to do the homework problems and also to be prepared for the exam, which is not for a few weeks, but anyway, there'll be an exam coming up. I think it's early February, is to read the chapter. So a lot of times students will ask, how can I do well in this class? Well, probably the most important thing of all is to read the chapter and take notes. Each chapter is probably going to take about 3 hours to read it carefully, read it, concentrate on reading the chapter. You don't have to do it all in one sitting. You can spread it out over a couple of days, but it'll help if you also take notes. So you should have a notebook which you use for Physics 231C and you don't use it for any other purpose. And for each chapter, you should take about 1 page of notes, both sides, mostly equations. So then you'll have in your notebook the most important equations from the chapter. And when it comes to doing the problems, you can just look back at that 1 page in your notebook to find accurate expression for each equation. And that'll be a lot quicker and easier than leafing back through the textbook and trying to find the equation in the textbook. And of course, on the exam, you're allowed to use a page of equations. So if you've already got the equations written down, that'll make it a lot easier to prepare yourself for the exam, because you're going to have to do that for chapter 2 and chapter 3 and chapter 4. So do it for each chapter as you're reading the chapter. So here's an example of a problem which is on problem set 1. A lot of students have already worked on problem set 1, so maybe you've already done this problem, but let's just see how to go about doing this problem. A small pebble is dropped from a platform. The initial height is h above ground level. Determine the time when the pebble hits the ground. In other words, how long does it take to fall to the ground from a height h? And it gives you the value of h, 16 meters. So a pretty high platform. So how long will it take? Well, you might guess 2 or 3 seconds. Now, the way to do most physics problems can be done using this general method. First, you draw a picture and label the picture with the variables, not in terms of their numbers, but in terms of their symbols. So let's see a picture. Here's a picture of the problem. You have this platform. It's at a height h. You drop the pebble. It falls down with an acceleration g. So there's the picture. You see, it doesn't have any numbers in it, just symbols. And then the second step is to write the necessary equations using the picture and using the symbols that are in the picture. So the pebble is going to accelerate downwards. The acceleration will be minus g. If you've read chapter 2, you know the value of g is 9.81 meters per second squared. The equation for height as a function of time with constant acceleration is y0 plus v0t plus a half at squared. It starts at the platform with v0 equals 0 at rest. It starts with height h, that's this 10.16 meters, and a is minus g. So you get this equation, and you want to know the time when it hits the ground. Well, when it hits the ground is here, So that's when y is 0. So these are the equations you have to use. And now it's just a matter of algebra to, to calculate the unknown. The unknown in this problem is t. So if I set y equals 0, that would be at the ground, when it hits the ground. I just get t is the square root of 2h over g, just using algebra. So t is the square root of 2h over g. And now the final step, you've now solved the problem by algebra, but you don't have the number. And what ln kappa is looking for is the number. So you have one more step, that's the fourth step, is to calculate this number with a calculator. So you have the square root 2 times h divided by g, square root of 2 times, this was 16 meters. So 2 times 16, g is 9.81. That's pretty close to 10. So it's approximately 2 times 16. And you also have to keep track of the units. So you get the right unit from ln kappa. The unit in the numerator here is meters. The unit of g is meters per second squared. So if we look at the unit, you see the meters cancel. I can multiply numerator and denominator by second squared. So I just get second squared, but take the square root. So the unit will just be seconds. And the number will be the square root of, well, what is it going to be? It's going to be 32 over 10, so 3.2. So it's the square root of 3.2 seconds. You have to give a number to ln kappa, square root of 3.2. Well, it's a little less than 4. It's a little less than 2. So if you do it carefully with your calculator, you should get this number accurately. It's a little less than 2 seconds. So that's a typical problem solved by this general method, which almost always is the best method to use in solving any of the homework problems in this class or the exam problems. So let's go to another example from problem set 1. Here's the problem. On the planet Kuzbane, if a pebble is dropped from height h, it falls to the surface in time t. And it's going to give you the value of these parameters. Let's say the height is 5,000 meters. Let's say the time is 1.768 seconds. Then what's the acceleration? So step 1 is to draw a picture. Well, here's a picture. Here's the cliff. You're standing on a cliff at a height h. You drop the pebble. It's falling down with an acceleration a. You're trying to figure out a. And at time t, it's at a position y. So there's the picture. Here's the equation. Y starts with velocity 0 because you just drop it from this point. So there's no v0t, but there's a half at squared. So that'll give you the height as a function of time. And you want to know, well, what you're given is the time to fall to the ground and also the height. So the unknown in this equation, where it hits the ground, is just a, because you already know h, you already know t. So now if you use algebra to calculate the solution of this equation, where you set y equals 0, you see a will be 2h over t squared. It's a lot like the previous problem, but there you are calculating the time. Here you're calculating the acceleration. And actually, if you say h plus a half at squared is 0, that means a has to be negative. Negative just means that it's falling downward. because I set up a coordinate system where the positive direction is upward. So it's just like the acceleration of gravity on the Earth, it's minus g. Well, here a is negative. It's 2h over g squared. And now you've done the algebra, so it's only a matter of calculating the number and the unit. You calculate the number with a calculator, and you calculate the unit by putting in the units in the calculation. So I have 2h, h was 5 meters. It was 1.8 seconds. Well, it was 1.768 seconds. So let's round it off. Let's round it off just to get an approximation. It's about 1.8 seconds, and that's squared. So now you have the answer in the form of a number with a unit. Now the unit you can see is meters divided by second squared. So that's meters per second squared. That makes sense because this is a acceleration. And now the number you usually would calculate with a calculator. If I just kind of estimate it, 2 times 5 is 10 divided by 1.8 squared. 1.8 squared is about 3. So it's about 10 over 3, which is about 3. So it's about 3 meters per second squared, and there's a minus sign. Now, I don't remember how the problem is written in ln kappa. The correct answer here might be negative 3 meters per second squared. You have to include the number, that's the 3. Get it more accurately. You have to include the unit, that's the meters per second squared. You have to include the sign to indicate that it's accelerating downward. So the answer here might be minus 3 meters per second squared, or minus 3.2 or something. It may not require the minus sign. It may be that the question means what's the size of the acceleration. So the way I read this problem, the answer would be negative 3 meters per second squared, with 3 calculated more accurately. But if that doesn't work, then try the answer without the minus sign. Because sometimes the way a ln kappa problem is written, the answer doesn't include the sign. So, if you put the answer in and it says wrong, maybe the first thing to try is just leave off the sign and see if that makes any difference. All right, so that's a second example in problem set. This problem set is due, I guess, next Monday. A lot of people have done parts of it. Let's look at one more example. Here's another problem from problem set 1. You have 2 cars on a highway. So you have on a straight road, one car is traveling at a speed v1 in the slow lane. That's his red car. The second car has a speed v1 in the fast lane. So that's his blue car. But the driver in the blue car wants to pass the red car, so he's going to accelerate and go past the red car. So let's say when the second car is 20 meters behind the first car, its acceleration is, the driver puts his foot on the accelerator and accelerates with an acceleration A. And the question is, how far will the second car travel when it begins to pass the first car? So step 1 of any problem is to draw a picture. Well, this problem already had a picture submitted with the problem, but you can draw your own picture in your notebook. That's probably better than just using the picture which is on the computer screen. So here's a picture. It shows the x-axis. Let's call the road the x-axis. So this is the direction of, maybe it's driving north. So it's driving north. All right, so the x-axis is pointing north. Here's the origin, some point. Let's take the origin to the point where the second driver decides to apply the accelerator. So at that point, we'll call that point x equals 0. And the first car is at that x equals 0. Sorry, the second car is at that x equals 0. Blue car. But the red car is 20 meters ahead. So on the axis at 20 meters, that's the coordinate of the red car. So now the red car continues at the same speed as it started with. This is given here, 25.5 meters per second. But the blue car starts to speed up with some acceleration, which is given. So that's given here. So here's the picture. Here's car one. Here's car two. Car one is the red car. Car two is the blue car. Car two starts behind car one. It accelerates, and at some point, it's just going to start passing car one. But of course, in the meantime, car one continues to move forward. So, they're both moving, but car two will be accelerating. Car one is just at a constant speed. So step one is to draw a picture. Didn't do that problem, but let's go over this problem. Step two is to write the equations. So let's write the coordinate for car number one. That's the red car. It's just its initial position, that's 20 meters on the axis that I set up, plus v1t. So that's constant velocity. With car two, it's initially at x equals 0. That's the way I set up the coordinate system, where the coordinate, the origin of the coordinate system is where car two is when it starts to accelerate. So its position is 0. Its speed is v1 because when car two decides to accelerate, they're moving at the same speed. And then it has an acceleration, so the additional distance is 1/2 at squared. So now you have two equations with two unknowns. No, you don't really even have two unknowns, because v1 is given and a is given. Now you have to apply some algebra. What you want to know is, where does car two start to pass car one? So where do they have the same coordinate? So where is the coordinate of car two the same as the coordinate of car one? So here's the coordinate as a function of time. There'll be some time when they have the same coordinate, where x2 is equal to x1. So let's look at x2, v1t plus 1/2 at squared, and set that equal to x1. That's 20 meters plus v1t. So I set these two equal. That's an equation now. v1t cancels on both sides of the equation. 20 meters plus v1t is v1t plus 1/2 at squared. So the v1t will cancel on both sides of the equation. And all I'm left with is 20 meters is 1/2 at squared. and A is given. So in this equation, it's just a matter of algebra to calculate the time. It's 2 times 20, 40 divided by A. A was 2.5. That's T squared, T sub P. The P here stands for pass. So T, the time of the pass, is the square root of 40 over A. Now A is 2.5. 40 over 2.5. Well, you have to use your calculator. No, A is not 2.5. A is 2.5 meters per second squared. So when you do the calculation in your notebook, you should keep track of the units. So I would have here 40 meters over 2.5 meters per second squared. Now the unit is meters divided by meters per second squared. The meters cancel, the second squared comes up into the numerator, take the square root, so the unit will be seconds, which is appropriate because you're calculating a time. But now what about the number? Well, this is 40 divided by 2.5. 2.5 is 100 divided by 4. Yes. So I think this is wrong. I don't know if this is wrong. I'm not sure about this. Maybe I have a wrong number here. Now, that's the time when the second car passes the first car. But that's not what the question is. The question is, how far will the second car travel? Well, that's given by this coordinate, where the time is the solution to this equation. I have here the solution 4 seconds squared, but that doesn't look right. So anyway, calculate this correctly and plug it into here to get x2. That's the distance that the second car has traveled. But I guess it says here about 100 meters. Let's see, V1 was 25 times 4 would be 100, plus a little bit extra because of the acceleration. So I don't know, I might have a mistake in the calculation here. I'm not sure this is right. It's the square root of 40 divided by 2.5. Let's see, 40 divided by 2 would be 20. 40 divided by 2.5 would be a little bit less than 20. It would be about 16. No, so I think I do have this correct. I have this correct after all. So that's the solution to that problem in the general method. You draw a picture. Here's the picture. You label it. You write down the equations using the labels in your picture. Then you apply algebra. And then you finally use your calculator to calculate a number with a unit. All right, any questions? I think I had one more problem to look at. Yeah, here's one more problem. Here's one more problem with a kind of a strange prefix, but the problem is this. A car on a straight road stopped at a red light. So here's the picture. Car on a straight road. Tommy, stop barking. It accelerates with a constant acceleration, 67 kilometers per hour. No, that's not the acceleration. It doesn't tell you what the acceleration is. The acceleration is the unknown, but it tells you that it's traveling at a speed of 67 kilometers per hour after traveling 142 meters. So you draw a picture. Here's the picture. The speed here is changing because after the light turns green, the car starts accelerating away from the light. But it's constant acceleration. So V is V0 plus AT. You need to have these equations for constant acceleration written down in your notebook. When you read the chapter, you should have seen these equations, which apply to all problems with constant acceleration. They never apply to problems that don't have constant acceleration. But anyway, you should know all these equations. They should be written down in your notebook already. One equation which is sometimes useful is this equation. V squared minus V0 squared is 2a x minus x0. Here's V as a function of time. Here's x as a function of time. But I can also write V to x. So if I put these together, I can get this equation which relates V to x. The change in V squared is equal to 2 times a times the change in x. So that'll be the problem, the equation to use here, because here I'm given the change in velocity and the distance. So the only unknown in this third equation is a. I have V squared minus V0 squared. Well, V0 is at the red light, so that's 0, is 2a times the distance. And now the unknown here is a. So by algebra, a is V squared over 2d. Here's V squared. But you better convert from kilometers and hours to the standard units of meters and seconds. So it's 67 kilometers, and a kilometer is 1,000 meters per hour, and an hour is 3,600 seconds. So here's V squared, where I've converted from kilometers per hour into meters per second. That's squared, and then divided by 2 times the distance. Distance should have been given 142 meters. So again, I have an answer to calculate, but it has two parts. It has a number and a unit. The number you can calculate with your calculator. The unit you can't calculate with your calculator. The unit you have to calculate by looking at the units in this expression. I have meters squared in the numerator divided by meters in the denominator. So that'll be meters. I have seconds squared in the denominator. So the unit will be meters per second squared, which is appropriate because I'm calculating acceleration. And now what's the number? Well, you have to use a calculator, or you can sort of estimate. It's not too far from 1, but use your calculator to calculate this number, get it accurately. It's about 1.2. Do it more accurately than that for ln kappa. Okay, so I've gone over, sort of the general idea of reading the chapter and taking notes, and then 3 problems. No, actually 1, 2, 3, 4 problems from the assignment. Any questions? This is how these Zoom meetings will go. I shouldn't have forgotten to start at 4 o'clock, but I was busy doing something else, and at 4 o'clock passed by and I didn't realize it. But normally we'll have these meetings 4 o'clock Friday afternoons, and I'll make some general comments about the equations from the chapter, and then I'll go over some example problems. These will be problems from the assignment, which are maybe a little more difficult than the average problem. So give you some ideas on how to go about doing those problems. And now I will stop the recording.